Okay. So we're going to talk about a reflection. A reflection is a transformation that takes a function and moves it across a line. Okay. Flips it across the line. And we can do that across the x-axis or the y-axis. Okay. So I want to kind of demonstrate here real quick. And you guys talked about this in geometry, or you should have. If you had me for geometry, you definitely talked about this. But you also did this in like 7th and 8th grade. Okay, but you did it with shapes instead of functions. If I give you a graph here of some point, let's say at this point right here is got an x value of like 3, 5. Okay. And this is on a piece of paper. So let's say that that's my piece of paper. And I asked you, can you fold this on that line right there? So you take your piece of red paper and you fold it on the x-axis, that blue line. Can you visualize where 3, 5 will touch or match up to on the rest of that paper? What quadrant, if this is quadrant 1, this is 2, this is 3, and this is 4, what quadrant is that point going to touch on? Quadrant 4, right? It's going to move, it's going to touch, if I fold it on that blue line, it's going to touch like right there, right? Does that make sense, everybody? Yeah. Okay. Now, when we do that, we say distance is preserved. This is called, in geometry, this is called an isometry. Now, you don't need to know that word, but that's what we mean by the idea that when I do a reflection, that the distance at that point is from the x-axis is the same in the reflection. And the distance at that point was from the y-axis is the same as that distance in the reflection. Does that make sense? So all those distances there that I just made with those blue braces are the same as what they were in the original. So this point here is still identified by the ordered pair 3, 5, but what is the y value? If I'm going from 0, 0, how do I get to that point? I got to go down, right? So what's that make this 5? Negative. Okay. So in geometry, we had a rule that said if you have the point A, B, where A and B are just any real numbers, and you did an x-axis reflection, then you would get A, the opposite of B. Okay. That's what we learned in geometry. And we had a rule that we probably wrote it like this. We wrote like capital R, and then we wrote at the bottom like x-axis. I was telling everybody what I was going to reflect it across. And then I said, if I start with the point A, B, it's going to turn into the point A, negative B. Have you guys ever seen that before? Okay. So if I gave you the point like, I'm going to do an x-axis reflection of like -4, 7. Okay. So that's A is -4, B is 7. Does that make sense? Then when you reflect it, that point is still A. So it's still -4. You don't do anything to it. But now the B becomes negative B. So B was 7, it becomes -7. Is that okay? Okay. That rule right there, what we talked about in geometry, is going to be the same thing that we talked about today, but we're going to use different notation. Okay. Remember that we're talking about functions. So this point is going to be developed by a function. So it's going to be an x value followed by a y value. But that y value, we know it comes from a function. So I'm going to call it f of x instead of y. Okay. So if that's that original point right there, then this point right here, when I do the reflection, is x, the opposite of f of x. Does that make sense? It's the same, it's using the same a and b, just different notation for a and b. Okay? A is now x, and B is now f of x. Okay? So what's that allow me to do? Well, coming here, we would have, the rule would look like y equals f of x. Down here, the rule is going to be y equals the opposite of f of x. And why do I say that? Okay? If you start with some function, okay, let's say I start with like y equals x squared. That's a function. And I want to graph y equals the opposite of x squared. Okay, f of x is my x squared. Does that make sense? The opposite of x squared now is the negative f of x. And all this tells me now, if you knew how to graph this, I knew how to graph that. And you know the ordered pairs that come off that. The ordered pairs that come off that, if I go x and y here, like -2, -1, 0, 1, 2, if you know those, they're 4, 1, 0, 1, and 4. If I just square that number, I get 4. Square that one, I get 1. Square that, I get 0, 1, and 4, right? If I know how to graph x squared, then graphing the opposite of x squared is taking these points and now all I do is I take these y values that were up here for x squared and I make them negative. So it becomes -4, -1, 0, -1, -4. And I can graph those, and that's going to give me my negative x squared graph. Does that make sense? Okay. So all these transformations here, guys, you guys, no matter what function I give you, if I give you like, y equals, let's go x plus 3 squared minus 5. Give you something like that. You don't write that down. But if I gave you something like that, you guys know that you can always, and this is what you learned in Algebra 1, you can always go back to this process and say, well, x is maybe 0, 1, 2, 3. And you can plug those in here and evaluate, right? And you create your table. That's the most basic way we've ever learned how to graph something. That's inefficient. That's a very time-consuming process, okay? And even if I did that here, let's think about this. This is going to give me a parabola, okay? But if I just graph those points, so I should get that graph right there. Does that make sense when I'm done? Okay. But if I just chose x values of 0, 1, 2, and 3, they're going to be these points. So let's go 0, comma, f of 0. We'll have 1, comma, f of 1. 2, comma, f of 2. And 3, comma, f of 3. Okay. So if I just plug these 0, 1, 2, 3s in and evaluated, I would get these 4, 11, 20, and 31s back. And it would just give me those 4 points. Does that make sense? Those are the only 4 points I would have. Well, if I connected those, would those 4 points give me that graph? Or if I connected those, would I only get that if I connected those 4? Does that make sense? Does that look, now it's part of, but is it that complete graph? Does that make sense there? Right? No, it's not, right? So you would have to know, okay, I can't just choose 0, 1, 2, 3. I got to choose like -1. If I choose -1, does it give me enough to say, okay, if I go -1, I would get that point E right there. Okay, well, that's still not showing kind of that turn in my graph, right? So then I would have to try 0. So let's go, or not -1, -2. Let's go f of, so -2, comma, f of -2. And I try -3, f of -3. And there I get the turn, but now I got to go one more, and I'd have to go -4, f of -4. And now I finally see enough points here. Enough points like A, F, G, and H to get that turn, to get that complete parabola, right? Okay. Normally, we don't know how far to choose those values if we don't understand what we're talking about right now. What we're talking about right now should eliminate us having to do this kind of guessing what my graph is going to look like to determine how many points and what points I need to plot. Okay. That's the whole benefit of learning what these transformations do, because if I use the transformations that we've already talked about, where we talked the other day, so if I start with x squared, okay, and I want to go to x plus 3 squared minus 5, the last two videos talked about getting that gray graph by starting with the idea of if 0, 0 is on the red graph, 0, 0 is on the red graph, then I should be able to find the point that corresponds or matches to that point on the gray one by knowing what these do, what these numbers here of 3 and negative 5 do to 0, 0. Okay? If I'm adding 3 to the x, we talked about in the last video that that is actually going to subtract 3 from your x value in your ordered pairs. Okay? So this sign is the opposite of what it's going to do. Okay? This here is going to, because it's negative, it's going to move my y value down. So I have a y value on the red graph of 0. This is going to move that y value down 5, so minus 5. Does that get me that point B to match up to point A? Are they corresponding? That make sense? This point here, if I go from A, move left 3, down 5, it gets me to its matching point on that parabola. Okay? There's another point, 1, 1, that exists on the red graph, red curve. Okay? If I take that point, 1, 1, okay, and subtract 3 from the x, and subtract 5 from the y, does it get me a point that is on the gray? Okay. Now I also know that there's a point x squared, on x squared, that is negative 1, comma 1. It's that point E right there. Well, if I start with that point, negative 1, and go back and say, okay, well, this plus 3 is going to move left 3, so subtract 3 from the x. And the minus 5 is going to move it down 5, so subtract 5 from the y. Oh, sorry, that was a positive one. Subtract 5 from the y, hit enter, and it gives me f, right? And now we can see that if I want to graph this curve right there, then all I need to know are these 3 points off the original parabola, and then how to move those, because that's going to then generate that curve, that turn, and I'm going to get most of my graph that way. Does that make sense? And that is much faster than trying to decide, okay, do I choose 0, 1, 2, 3 and plug that in and just get kind of these points here and then say, okay, well, now I need to try negative 1, negative 2, negative 3, negative 4 until I get that curve or that turn. Using transformations is so much faster, so much easier. Okay? So one of them, like I said, was this reflection. Okay, if we start with x squared, going off the points for x squared, and these are things, guys, that my hope is that we commit these points to memory. Okay, whenever I talk about x squared, I want those 5 x values to be in the forefront of my mind. And then when I square them, they're pretty easy to square, right? So then I'm going to plot 0, 0, 1, 1, into 4, negative 1, 1, negative 2, 4. Even if you want to go a little bit further, you want to go 3, 9, and negative 3, 9, that's fine. My parabola kind of hard to draw with this tablet. But smooth curve through those points and you get your parabola, right? Okay. Well, going to now over here, the only difference is that now you've taken your x squared and you've got a minus out in front, right? You've negated the entire thing. But this is a rule for getting y values. Okay, and all this is, the only difference here between that one there and this one here If I just, the highlighted parts are the same, right? Those are rules for getting the y value. Well, this says now your y value is just the opposite of what it was over here. Okay, so if I go my x value of -2, -1, 0, 1, and 2. Okay, if I squared those, I got 4, 1, 0, 1, and 4. So that's the same list as right there. But what should be different? The y value should be the opposite. So when I plot those, 0, 0, now it would be x is 1, -1, 2, -4, -1, -1, -2, -4. Do 3, 9, 3, -9, and -3, -9. And connect those. Try to connect them. Okay. Does that green graph on the right look like the x-axis reflection of the one on the left? And that's the hope that we realize that in the future then, when I'm asking you, what does x cubed look like? And then the next question, well, what's negative x cubed look like? You can make that jump right away. And because you know what x cubed looks like, you automatically know what negative x cubed looks like. Okay? Do you have a question?
I was going to ask if you could zoom out.
Oh, yeah. That good or?
Yeah.
A couple more times. So if I go, I'm just going to put some points in here. Doesn't matter. And type in some garbage here. Doesn't matter to you either. And I look at that graph right there. Okay, and it's pretty nasty in the y direction, so let's see if that fixes it. Still kind of, that's all right. All right, so we get that graph right there, okay? Don't worry about any of these points. Let's actually get rid of all of them. Okay, so I got this function f of x. Okay, I'm going to create a new function. I'm going to go g of x, and I just don't even worry about that part. Okay, it's just that I have to do for the coding of this program. But if this is f of x, let's multiply it by negative. Let's put a negative out in front. And you see what it did to that graph. It took the purple graph. And does it look like we folded on the x-axis and the purple graph landed on the red one? Okay. The only thing that changed is if I were to look at so this line I'm putting in to allow me to find some x values. Okay, so if you look at these 2 points, I and J, okay, and all this line is doing for me is showing you points that got reflected. Does this point right there, is this I coordinate, -2.45, comma 44.23, is that ordered pair the same ordered pair as this one, but the y values are only opposite? That make sense to everybody? As I move that through, let's go find another random x value. There's a random x value of 1.57. On the purple graph, we get a y value of 11.71. On the red graph, it's still the same x of 1.57, but the y coordinate now is just the opposite of what it was up here. Does that make sense? Okay, and every point on there is the same. No matter what my graph looks like. So I can completely change that graph by moving some of these points around. But that relationship, no matter what, always exists for reflections across the x-axis. We cool with that? Okay. In your homework every once in a while, they'll give you like a generic function. They'll give you, let's put a point at -4, 2. Let's put a point at 0, 5. Let's put one at 3, 5. 4, 3. And then let's go over to like 7, 8. So we'll plot those, and I'm going to connect those with a line. Or with lines. And they'll call this f of x, they'll call it a function, which it is because it passes the vertical line test. So every x value has one and only one y value. Okay. So in the image, they'll say that this is f of x. And then they ask you, you make what the opposite of f of x looks like. Okay. Well, if we remember, so if this is y equals f of x, then what does, let's do this in blue, y equals the opposite of f of x, what should that look like? Well, we should know that the rule, what it does, is all it does is changes the y value, right? So if this point here is -4, 2, what's it going to become? If it's -4, 2 on f of x, then it's -4, -2 down here. If this point is 0, 5, it's going to become 0, -5, right? If this is 3, 5, it's going to become 3, -5. This one here is 4, 3, so it becomes 4, -3. And then the one at 7, 8 becomes 7, -8. And now we can connect those with our line. And does that image look like the reflection of what we started with? Okay. Now that's using a generic function. What kind of stinks about that is we don't have a rule, a real nice rule like x squared or square root of x or something like that can be used to make this. Okay. So we'd have to do it in like little partitions or segments. But the relationship about what happens to the y values is the same. So if I want to do this with, so that's working with a reflection across the x-axis. Let's take, and I don't think I put this on your notes. Let's see here. Is there anything on your notes that says something about f of -x? Oh, you guys didn't print them off?
Are you talking about the ones we got during?
But these should have been, these are on Schoology. My hope was that when you guys were watching the videos, you had printed these off first. All right, let's talk about this then.